Hello, in this class let us discuss the impurity conductivity or extrinsic conductivity. If certain impurities are added to a semiconductor, its conductivity increases drastically. Okay, for example, one boron atom is added to 10 raised to 5 silicon atom. Okay, so 1 in 10 raised to 5 silicon atom is replaced by a boron atom, then the conductivity increases by 10 raised to 3 times. Okay, so this is one example. So therefore, adding impurities to a semiconductor increases its conductivity. So this addition of impurities to a semiconductor for increasing its conductivity is called doping. So doping is deliberate addition of deliberate addition. So we are adding for increasing the conductivity. Deliberate addition of impurities to a semiconductor for increasing its conductivity. This is called doping. Okay, so let us discuss the effect of adding impurities to germanium or silicon. Okay, germanium and silicon. You know what is germanium? Germanium and silicon have these 4 valence electrons. There are 4 electrons in the valence shell, so they form 4 covalent bond with the 4 nearest neighboring silicon atom. Okay, so if you take silicon atom, so a silicon atom forms 4 covalent bond with the other 4 silicon atoms. Likewise, all these silicon atoms make covalent bond with the 4 nearest neighbors. Okay, so they form a 3-dimensional array of silicon atoms. So this is a tetrahedral bond. This is tetrahedral bond. The tetrahedral angle is 109 degree 28 minute. Okay. Now, if a pentavalent impurity, that means impurity atom with 5 valence electrons, impurity atom is added, then a silicon atom is replaced by the pentavalent impurities like phosphorus, arsenic, antimony. These are pentavalent impurities. So if we add this thing in this ratio, very small ratio, then a silicon atom is replaced by this atom. So it has 5 electrons in the valence electron. Therefore, there will be, so then so this is the case. Okay, so arsenic has 5 electrons, so there will be one excess electrons left over after establishing 4 covalent bonds. Okay, so for arsenic there are 1, 2, 3, 4 and 5 electrons. So this, the 5th electron is excess electron. So that contributes to the conductivity of the crystal. Okay, so by adding impurities we can one can enhance the conductivity of semiconductors. So here these pentavalent impurities are called, donors, donor impurity. Okay, so these are called a donor impurity because they donate one electron to the conduction band. So this excess electron is donated to the conduction band. So it goes to the conduction band. It is a free electron, so it is in conduction band. So that's why it is called, these pentavalent impurities are called donor impurities. And corresponding semiconductors are called N-type semiconductor. N-type semiconductor. Now, next is if trivalent impurity is added, like boron, aluminum, gallium, indium. So these are trivalent impurities. If they are added to the silicon, then they accept electrons from the valence band in order to complete the covalent bonds with the 4 neighbors, 4 neighboring atoms, leaving holes in the band. Okay, so a hole is created in the valence band because of this trivalent impurity. Okay, so these trivalent impurities are called acceptor impurity. acceptor atom or acceptor impurity. Okay, so trivalent impurities are acceptor impurities because there is one lack of electron in the valence band, one hole in the valence band. So therefore these are called p-type semiconductors. Okay, so n-type semiconductor and p-type semiconductors are the doped semiconductors, impurity added semiconductors. When pentavalent impurities are added to a semiconductor, then such type of semiconductors are called n-type semiconductor because these impurities add one electron to the conduction band, or they donate one electron to the conduction band. Whereas if trivalent impurities are added to semiconductor, then such semiconductors are called p-type semiconductor, and these trivalent impurities are called acceptors. Now let us discuss the donor states or donor level. So if pentavalent impurity is added to semiconductor, then impurity atom replaces the normal atom. Actually, this is tetrahedral bond. It's not like 90 degree, it is 109 degree. Here there will be one excess electron, and this arsenic atom, the pentavalent atom, act as a positive atom, positive because this electron is free. So this electron revolve around this arsenic positive arsenic ion or the pentavalent ion. So let us calculate the what is the ionization energy of the electron. Let us consider the ionization energy of the donor atom. Okay, so here the ionization energy of the donor atom is represented by ED. So this can be obtained by Bohr atom model of hydrogen. Okay, the hydrogen for hydrogen atom, the ionization potential is given by EH is equal to, if so this is similar to a hydrogen atom because this electron is revolving around this impurity ion, so it is similar to hydrogen atom where electron is revolving around a proton. Okay, okay, in the first orbit the ionization potential is 13.6 electron volt, or ionization energy is 13.6 electron volt. This is given by the expression m e raised to 4 divided by 2 times 4 pi epsilon 0 h cross whole square. Okay, so this is the ionization potential of hydrogen atom, 13.6 electron volt. So in this is in joule. So if we convert it to electron volt, this will be 13.6 electron volt. So if we apply 13.6 electron volt, then an electron is detached from the hydrogen atom. Similarly, so what is the energy required to release this electron from the potential of pentavalent impurity? So that is given by ED. So here ED is equal to, here the here mass m is the mass of electron in this case. Okay, but in the case of this impurity atom, the mass of electron is replaced by effective mass of electron in the periodic potential. So this is given by me star, and charge of electron is e only, so e raised to 4 divided by 2 times 4 pi epsilon 0. And so in a hydrogen atom we are considering epsilon 0 because it is in vacuum, the medium is vacuum, but the electron here is in a semiconductor, so we have to consider the relative permittivity also, or the dielectric constant. So for pi epsilon 0, epsilon r h cross whole square. Okay, so this is for electron in the impurity. excess electron in the impurity atom. Okay, so we can calculate the ionization potential using this. Here Me is the effective mass of electron and epsilon r is the dielectric constant of the semiconductor. Or let us change this equation in terms of the hydrogen ionization potential. That is, here Me can be written as Me divided by M into M e raised to 4 divided by 2 times 4 pi epsilon 0 h cross square. So this epsilon r can be taken out, epsilon r square. Okay. So this thing is the ionization potential of hydrogen. So this is equal to Me divided by, so this is Me star divided by M epsilon r square into 13.6 electron volt. So the ionization potential of the donor impurity is given by Me star, that is the effective mass divided by mass of electron divided by the square of the dielectric constant times the ionization potential of the hydrogen atom. Okay. So if you consider, if you want to calculate the ionization potential of this thing, the effective mass of electron in germanium is about 0.1 mass of electron. Okay, 0.1 m, and in silicon it is Me star is given by 0.2 mass of electron. So effective mass of electron in this in germanium is about 10% of the mass of electron. Okay, this is 20% of mass of electron is in the in silicon. This is in germanium. What is the ionization potential? So Ed is equal to, and also the dielectric constant of germanium is about 16, whereas for silicon it is for silicon it is around 12. Okay, it's about 12. So therefore this ionization potential will become point 0.1 divided by 16 square into 13.6 electron volt. So this is about around 5 milli electron volt. 5 milli electron volt is very small energy. So the ionization energy of hydrogen atom is 13.6 electron volt, whereas the ionization potential of electron in the impurity atom in the n-type semiconductor is about 5 milli electron volt. Therefore, compared to hydrogen atom, the ionization potential of the electron in the donor atom in a semiconductor is very small. Now, the radius of electron around the impurity ion is given by D is equal to 4 pi epsilon 0 epsilon r h cross square divided by Me star into E square. Okay, whereas the radius of hydrogen atom is given by 4 pi epsilon 0 h cross square divided by Me square. Okay, which is equal to h square divided by pi Me square. This was the radius of hydrogen atom in the ground state. It is about 0.53 angstrom unit. This can be written in terms of the radius of hydrogen atom. Therefore, we can write 4 pi epsilon 0 h cross square divided by m e square into epsilon r divided by m e star by m. Okay. So this is equal to 0.53 angstrom unit into epsilon r divided by m e star divided by m. Okay. The radius of the electron of the donor impurity atom is given by 0.53 into epsilon rs 16 divided by 0.1. So this is equal to this is about 80 angstrom unit. Okay. So this is for germanium. For silicon, this is about 30 angstrom unit. Okay. Okay. So the radius of orbit of electron around impurity ion is very large compared to the radius of hydrogen atom. So that means because of this dielectric constant and effective mass, the Coulomb interaction between this electron and the ion is greatly reduced. Okay, so because of that, this will contribute to the conductivity. So these electrons become conduction electrons. Now let us draw the donor level for a normal semiconductor. So this is the valence band edge. So let me put this as 0, and the conduction band edge is EC, that is, so this difference is called EG. So here EG is of the order of some electron volt, few electron volt, okay, 5 electron volt, 4 electron volt for a semiconductor. When an impurity is added, there will be an intermediate level. This is the donor level. So this donor level separated from the conduction band by a small amount of energy. So that is the ionization energy ED, which is of the order of few milli electron volt. Okay. So this is in electron volt. This is milli electron volts. So it is reduced by a factor. The energy gap actually reduced by a factor of 10 raised to minus 4 to 10 raised to minus 3. Okay, so this is very small compared to the energy gap. So this is the donor level. So when an impurity is added, electrons can be taken to the conduction band very easily. Now let us draw the acceptor level also here. When a trivalent impurity replaces the normal atom in silicon or germanium, then there will be a hole created in the valence band. Okay. So here the trivalent impurities such as aluminium, boron, gallium, etc. So these are called acceptors. So if these impurities are added to silicon or germanium, they are called acceptors because they accept electrons from the valence band of the silicon or germanium, leaving holes in the valence band. Okay, so if a boron replaces silicon atom in silicon crystal, then there will be lack of one electron to complete 4 covalent bond with neighboring nearest neighboring silicon atoms. Therefore, a hole is created in the silicon valence band. Here also Bohr model can be applied. Now let us draw the acceptor level here. This is the valence band edge and this is the conduction band edge. Okay, so the difference between conduction band edge and valence band edge is Eg, the energy gap. which is of the order of few electron volts, and there is a intermediate level. So this difference is called the ionization potential of ionization energy of acceptor atom. Okay, and this is the acceptor level.